Hello everyone, welcome back to my YouTube channel. Today we are going to discuss an important topic which is the principle of equivalence, curvature of space and black holes. Let's begin with the principle of equivalence. We usually define mass in two ways. Inertial mass. We might say that inertial mass represents a resistance to any force, and gravitational mass, which determines the pull of gravity. Surprisingly, they are always equal, a fact confirmed with extreme precision. Einstein called this the principle of equivalence and used it as a foundation for his general theory of relativity. It means this: there's no way to tell if a force you feel is from gravity or just acceleration. Imagine you are in a spaceship far from any planets. If an apple falls, is it gravity or is the ship accelerating upward? You won't be able to tell. So, if you were far out in space and an apple fell into the floor of your spacecraft, you might assume a gravitational force was acting on the apple. But it would also be possible that the apple fall because your spacecraft accelerated upward relative to an inertial system. The effects would be indistinguishable according to the principle of equivalence because the apple's inertial and gravitational masses that determines how a body reacts to outside influences are indistinguishable. Here's the twist. Light is also affected by gravity. Imagine you shine a beam of light across an elevator that's accelerating upward. To an outside observer, it moves straight, but to someone inside, the beam curves downward. This proves that gravity bends light. The principle of equivalence can be used to show that light ought to be deflected due to the gravitational force of a massive object. If a light beam enters a hole in the side of the elevator, the beam travels straight across the elevator and makes a spot on the opposite side if the elevator is at rest, as shown in figure A. If the elevator is accelerating upward, as is shown in figure B, the light beam still travels straight as observed in the original reference frame at rest. In the upwardly accelerating elevator, however, the beam is observed to curve downward. Why? Because during the time the light travels from one side of the elevator to the other, the elevator is moving upward at ever increasing speed. According to the equivalence principle, an upwardly accelerating reference frame is equivalent to a downward gravitational field. Hence, we can picture there the curved light path in figure B as being the effect of a gravitational field. Thus, we expect gravity to exert a force on a beam of light and to bend it out of a straight line path. So, if light bends, what does that mean about space? Einstein proposed something revolutionary. Gravity doesn't just pull, it warps space at itself. Massive objects like stars curve their space around them. The curvature is greatest near very massive objects. To visualize this curvature of space, we might think of space as being like a thin rubber sheet. If a heavy weight is hung from it, it curves. The weight corresponds to a huge mass that causes space to curve. A black hole is a collapsed star with so much gravity that nothing, not even light, can escape it. It's like a bottomless pit in space. Anything that gets too close gets pulled in forever. One likely possibility is a giant black hole at the center of our galaxy and probably at the center of our other galaxies. Einstein's theories predicted them, and in 1919 scientists proved space curvature by measuring how starlight bent near the sun during an eclipse. So, from falling apples to black holes swallowing light, the universe is full of incredible forces. Thanks to Einstein and the principle of equivalence, we now understand the invisible warping of space itself. Thank you for watching.